Hello kids, what we are going to study today is the chapter called sound. Most of you have studied this in school, but this is just a very brief recap about what sound is and how is it produced and what are characteristics of sound. So what we shall be doing in this chapter is how is sound produced, how is sound propagated, characteristics of sounds, in which we will be talking about its amplitude, frequency, and how does it determine loudness and and pitch and also about timbre, that is the quality of sound. Then we shall also do a reflection of sound and something called echo and reverberation. We shall be talking about them in detail in the parts to come. So what is wave motion? First of all, we must have studied about translatory motion. We must have studied about the rotational motion. So what is translation? When the body moves in a straight line path, then there is a translation of a body. What is rotational motion? When a particle goes in a circular path, or I'll say the particle spins, is rotation, like rotation of earth, rotation of a top. When we talk about vibratory or oscillatory motion, the first thing that should come to our mind is that it should be a to and fro motion. Any to and fro motion is vibratory, about a mean position. There is a very slight difference between periodic motion and vibratory motion, in which vibratory motion is basically about a mean position and periodic motion is something which happens again and again. For example, the rotation of earth around sun is periodic, it is not vibratory or oscillatory. But swinging of a pendulum, when pendulum does a to and fro motion about the mean position, it always comes to the mean position, it always returns to the mean position back again. So wave, if I say in layman terms, wave is generally a collection of particles and it is basically the vibration of collection of particles. If I talk about pure physics in it, then I'll say wave is a collection of particles doing simple harmonic motion. But that will be very hard to understand. So in a simple, in another simple terms, in your standard in class 9th, I'd rather say wave is nothing but the transfer of energy in a medium. When energy goes through a medium, it disturbs the medium temporarily and then the medium comes back to its original position. So wave is nothing but it is the propagation of energy through a medium. When it passes through the medium, it disturbs the medium, but again the particles will come back to its original position. So what kind of waves are we going to study in this chapter? Just we shall take a recap of what we have understood in our previous classes also, like in grade 8th also we have studied a little bit about sound and waves. So waves are basically of two types. One is transverse wave and the other is longitudinal wave. Longitudinal means along length. Alright, longitude means along length. And transverse wave means it is perpendicular to motion. Here in this context. So when a particle is moving to and fro in the direction of propagation of wave, then such a wave is called longitudinal wave. For example, suppose, let us give an example of sound. If I speak something, then the air particles around me will compress, then they will expand, then again the particles which have expanded are going to collide with the nearby particles or the particles ahead in the path, again it's going to compress, then again it is going to expand. So this is called compression and rarefaction. So when it compresses, it is called compression. When it expands, it is called rarefaction. So longitudinal waves generally travel in the form of contraction and rarefaction. You must have also seen how the slinky moves, how a wave in a slinky moves. If I push a slinky from one side, the slinky will contract, expand, contract, expand, contract and expand, and that is how the wave is transmitted along the length. How is it transmitted along the length? The to and fro is also happening along this direction and the wave is also moving in the forward direction. Hence, the type of wave in which the vibration of particles is in the same direction as is the direction of propagation of wave is called a longitudinal wave. So in simple terms, I can say if the direction of vibration and direction of motion of the wave is same, such kind of wave is longitudinal wave. The classic example of it is sound wave. And how does these waves travel? They travel in the form of compressions and rarefactions. First, They will compress. When the particles compress, then they will collide with each other and then they will expand. When they expand, they are going to collide with the nearby particles. Again, the nearby particles are going to compress and expand. This is how the wave will get transmitted. In compression, what is happening? In compression, the density increases, pressure increases. In rarefaction, the density decreases and pressure also decreases. Alright? The sound is a form of wave and longitudinal wave, and when we try to draw a graph of pressure or density on y-axis and distance on x-axis, we will see that the pressure will first increase, then decrease, then increase, then decrease, and this negative means expansion in the backward direction. Alright, and 0 is, what does the 0 on the line signify? The 0 on the graph signifies that now the air is in normal state. Before expansion or contraction, when the air was in the normal state, when the compression starts to happen, density increases. When it expands, the pressure becomes lower than the normal pressure also, because now it is expanding. So that is why we are taking it as negative pressure or negative density. Negative does not mean that the pressure has become negative, or negative does not mean that the density has become negative. The negative here means that initially, say my height is say 5 centimeters, or I'll say my height is 1.5 meters. Somebody who has a height of 1.6 meters, according to me, is positive height. Somebody who has height of 1.4 meter is below me, so I'll be saying his height with respect to me is negative. So that is what is drawn in this graph. This negative here, the negatives here are not meaning that the pressure has become negative or the density has become negative. It just means that when we are plotting pressure, initially the pressure was 0. So the red line which I have drawn indicates to 0 pressure or the normal pressure at room temperature. Now when the compression will start, the density increases. After compression, when the expansion happens, now in expansion the particles have gone far away from each other, farther than they were in the normal state. When they have gone farther than they were in the normal state, the pressure has become lower than the initial pressure, which was when at a normal room temperature and pressure, what the pressure was. Now the pressure has gone in expansion below that pressure. That is why we are taking it as negative with respect to that. I hope that is clear. That is why we are drawing this kind of sinusoidal wave. Sinusoidal wave is nothing but a sine wave, which you do not have to know at this level. Let us go ahead. Now sound also needs a medium to propagate. From this wave, I also want to tell you something. There are certain things which I want to show you on the wave. So these points are called crests, and these points are called trubs, the bottommost points. What is wavelength? Wavelength is shown by this symbol called lambda. This is pronounced as lambda. So if you say in simple terms, the length of entire wave is called as wavelength. But I can also say that the distance between two consecutive crests or the distance between two consecutive trubs is wavelength. Between two crests also is wavelength, and between two trubs also is wavelength. If you want to show it on the graph, then I can show it like this also. I'm going to highlight it for you. Even this is wavelength. From here, if I start like this, and this entire wave, this also is wavelength. But that is just for the sake of definition, we say that the distance between two consecutive crests and the distance between two consecutive trubs is wavelength. Alright. There is another thing which I want to tell you, that you can see that this displacement, maximum displacement, even at top and bottom, is called amplitude. The maximum displacement from the mean position is called amplitude. We shall be talking about this in the coming part of the chapter. Then, sound requires a medium for propagation. Without any medium, the sound will not propagate. We have a classic example for this, which is the bell jar experiment. That if I put a bell inside a jar and I suck all the air out, there is no medium inside the jar, and now if I blow the bell or if I ring the bell, you will not be able to hear the sound of the bell. In the first case, what I have done, the jar is filled with air and then the bell is rung and you can hear the sound of the bell. In the second case, what I have done is I have sucked out all the air from the jar and the bell is now rung inside the jar. You will not be able to hear the sound of the bell outside the jar, because sound needs medium to propagate. And one more thing, the velocity of sound in solids is greater than velocity of sounds in liquid is greater than velocity of sound in gas. This thing also you should keep in mind. Since the Solids, the particles are very close to each other. The energy transfer is taking place very quickly. In liquids, the particles have a considerable amount of separation, because of which the sound is taking some time to transmit the energy between two successive collisions. In gases, the particles are far apart, so when the collision is taking place, it is compressing, then expanding, compressing, and then expanding. So the sound is slowest in gases. Generally, the speed comes out to be about 330 to 344 meter per second, generally in gases. Now, what are transverse wave? The simplest example of transverse wave is, say, if I tie a string, say a rope, gym rope. You have seen a gym rope. So you must have seen that people try to generate waves on gym rope, and the waves go like this. After some period, some point of time, you will see the wave has gone here. After some time, you will see that the wave has gone here. So what are you seeing? That the particles here are moving in upward direction. The wave is going in the forward direction. The particles of the string are vibrating perpendicular to the direction of propagation of wave. This is the definition for transverse wave. So what is transverse wave? The type of wave in which the vibration of particles is perpendicular to the direction of propagation of wave is called a transverse wave. Light is a transverse wave. It does not need a medium for propagation. And one classic example of transverse wave is your string wave. The wave on a string. Now if I move the string, what will happen? The crests and troughs are going to be generated, which are perpendicular to the direction of propagation of wave. Alright. Water waves are also an example of transverse wave. You must have seen ripples generated on water. If the water is calm and you throw a stone in the water, in the calm water, what will happen? You will see that the ripples start to come. They start to flow in this way. No? After some time, you will see that the ripples are going up and down, up and down, up and down. You must have seen this happening with the waves in a sea also. That a boat moves up and down, up and down. That is because of the transverse nature of the wave in water. Light is an example of transverse wave which does not need a medium for propagation. So this is a slinky experiment. Now if I try to give some force to the slinky in the upward direction, then I'll see the slinky is moving like this. Whereas if I try to push the slinky in forward direction, then the slinky will compress, then it will expand, then it will compress, then it will expand, and it will go in the form of longitudinal wave. Alright, if I try to give a motion to the slinky like the way I give the motion in a gym rope, then it is going to show a transverse wave. This is just an example of showing it. So what a mechanical wave, and based on the medium of propagation, the waves can be classified into mechanical wave, in which medium is required, and non-mechanical wave which do not need any medium for propagation. For example, water wave is a transverse wave. Gym rope, the wave on a string, is a mechanical wave. Sound is a longitudinal mechanical wave. Slinky can be both mechanical as well, is a mechanical wave because slinky is a medium itself. Then all the radiations are non-mechanical. Radio wave, X-ray are all non-mechanical. Even light is a non-mechanical wave, which is an electromagnetic wave, and it is a transverse non-mechanical wave which does not require any medium for propagation. How is sound produced? So sound is produced by vibration of anything. Anything which vibrates or oscillates about its mean position. See, there is a big confusion about what oscillation and vibration is. Vibration is an oscillation with a very small amplitude. Means very small, or I'll say movement from the mean position is vibration. Quick oscillations are vibrations in simple terms. Which has got very less displacement from mean position, which is happening very quickly, are vibrations. So vibration is a special type of oscillation in which the to and fro movement is taking place very quickly. Or in other words, I'll say, to be more precise, I'll say vibrations are special type of oscillations in which the amplitude of oscillation is very, very less. Very less displacement from the mean position. So the rapid to and fro motion of an object is called vibration. In humans, the vocal cords which are present above the voice box, the larynx, the air from the lungs, see, these are two vocal cords, okay? And this is the windpipe. Now, so windpipe passes through the voice box, and the voice box, above the voice box, we have two strings attached which are very close to each other. As soon as the air blows through lungs into it, what will happen? These strings will start to vibrate. When these strings vibrate, these vibrating strings are going to produce sound, and that is how humans produce sound, by the vibration of vocal cords. And we also said about this thing that sound travels in the form of compressions and rarefactions in a medium. The air near to your mouth will first get compressed, then it is going to push the other particles near to it, and that is going to get compressed, and then it is going to expand and come back to its mean position. The particles away from it are going to keep on compressing and rarefacting and compressing and rarefacting, and that is how sound travels. What are characteristics of sound waves? This, which I had already told you before. First is wavelength. Very simple. The length of a wave is called wavelength, or I'll say the distance between two consecutive trubs and two consecutive crests is wavelength. Then time period. Now suppose the wave is this much. Okay, I'm just shading here the diagram here. The time taken to complete one oscillation is called a wave. Is called time period. Simple. The time taken to complete one oscillation is called time period. The length of one wave, or in other terms I can say distance between two consecutive crest or two consecutive trough is called wavelength. Now since it is length, its SI unit will be in meters. Time period is time taken to complete one wave in simple terms according to the diagram, or I'll say the time taken to complete one oscillation. One oscillation is one to and fro movement. Complete to and fro movement is called one oscillation. So the SI unit of time period is seconds. Then we have frequency. Frequency and time period have a relation. Now see, I'm going to show the how this frequency and time period are related, and you might get numericals on this in your examination, because this is the numerical part: wavelength, frequency, time period, oscillation. So time period is time taken to complete one oscillation, and frequency is number of oscillations in 1 second. So if it takes t time, in t time how many oscillations take place? One oscillation takes place. In t time, one oscillation takes place. In t seconds, t is the time period. So in t seconds, one oscillation takes place. So in 1 second, how many oscillations will take place? It will be 1 by t. So 1 by t oscillations are going to take place in 1 second. And what is this number of oscillations per second called? This number of oscillations per second is only called as frequency, which is shown as small f also, or sometimes it is also shown as small nu. So frequency is 1 upon time period. This is the relationship between time period and frequency. Now what is the SI unit of frequency? Since frequency is equal to 1 upon time period, the unit becomes 1 upon second. The unit of 1 upon second is second inverse, and this second inverse is nothing but it is also called as hertz. So the SI unit of, to give some respect to the scientist hertz, we have given this SI unit as hertz for frequency. Alright. What does this wavelength? There is another thing called amplitude. Amplitude is the maximum displacement from the mean position. This is amplitude, this is amplitude, this is amplitude, this is amplitude. In the waves up and below, the top and below, you are seeing that this is having more frequency, because there are more number of oscillations taking place in 1 second. This is having less frequency. Alright, now what does it determine? What does amplitude determine? Amplitude is the maximum displacement from mean position. Since it is displacement, so its SI unit will again become how much? It will be meter only. If the amplitude is more, then the loudness of sound is more. Okay, greater the amplitude, greater the loudness. For example, I have a wave like this, and I have another wave like this. Both of them have the same time period. That is why both of them will have the same frequency, but the first one has got more amplitude. Since the first wave has got the more amplitude, that means it will be louder as compared to the second wave. Then we have frequency also. How does frequency determine the sound? I mean, what characteristic does frequency give to sound? That is, in the first case you are seeing that more number of oscillations. Let us count the oscillations. It is 1, 2, 3 and 4. 4 oscillations here, 1 and 2 oscillations. So here the number of oscillations per second is 2, so the frequency is 2 hertz. Here the number of oscillations, say this is 1 second. Let us consider this entire time is 1 second. So here the frequency is 4 hertz. Which among these has highest frequency? The second one. If the frequency is higher, frequency determines pitch or shrillness of sound. Pitch or shrillness of sound. What does this thing mean? That the sound will be more sharp. I'd rather say baby, when a baby cries, it generates, the vocal cords are very thin, because of which the pitch is very high. The shriller is the sound. More is the frequency, the shriller is the sound. And less the frequency, less shrill is the sound. So there is a relationship between the thickness of a string also. You must have seen that the strings of a guitar are in the sequence E, A, D, G, B, E. So the first E is the very thin string and the last E is the thick string. Both of them have the same sound, E, but the frequency produced by the lower one, which is the thinner string, will be more, and the one which is produced by the thicker string will be less. Men have thick vocal cords, because of which they have got lower pitch. Lower pitch means the number of oscillations take more time to take place, whereas the one which is thin will take less time to take place. Less number of oscillations per second for the thick string, low pitch. More number of oscillations per second for a thin string, high pitch. So frequency determines pitch, amplitude determines the loudness of the sound. Now we have velocity. Velocity is the, see, when we are talking about amplitude, we are talking about frequency, we are talking about wavelength, these are all about the wave, but the wave also is traveling in a medium, no, in some direction. So that velocity of the entire wave is called the velocity of wave. And how do we calculate velocity? So the simplest way is velocity is equal to displacement upon time. Am I right? This is all we have known. So how much is the displacement of the wave in one cycle? Wavelength. How much is the time taken for the wave to complete one cycle? Time period. So wavelength, frequency is equal to wavelength upon time. But we also know that 1 upon time period, but 1 upon time period we have just studied is frequency, or small f. So 1 upon t from this equation will become lambda into 1 by t. So lambda into 1 by t will become how much? It will become 1 by t will become frequency. So it will become lambda into f. So what formula did we get? Velocity is equal to lambda by t is equal to 1 by t is frequency. It will become lambda into f. So this is the relationship between frequency, wavelength and velocity of sound. Obviously the velocity will come out to be in meter per second. Alright, Newton gave this equation to find the velocity of sound. We will be studying about this thing in kinetic theory of gases or thermodynamics in grade 11. So velocity of sound comes out to be in air somewhat about 334 meter per second. See, here there is another interesting thing to note, that at 0 degree Celsius the speed of sound is less. At 22 degree Celsius the speed of sound is more. Why is that? Because as temperature increases, the kinetic energy increases, the particles are now moving fast. We have also read this thing in chemistry. I am pretty sure that the smell of hot food or the warm food which is kept at the corner of the room is spreading quickly throughout the room, whereas the cold food taken out of a fridge, we are not able to get the smell of that food. Why is that? Because the vapors which are coming out of hot food have got more heat, because of which they have got more kinetic energy. So more is the temperature, more is the kinetic energy, the particles are moving quickly, because of which the speed of sound varies. In gases, more is the temperature, faster is the sound traveling. There is a classic example you should know here. In water it is about 1450, in glass it is about 5600. So velocity of sound in solids is much greater than velocity of sounds in liquid, is much greater than velocity of sounds in gases. You must have also seen that for diamond it is 12,000 meter per second, because diamond is one of the hardest known things in the entire earth. And it is hard because the particles are very closely spaced, very, very dense. That is why the sound is traveling at a very faster pace. So we have already talked about this, that frequency determines the shrillness of the sound. More the frequency, more the pitch, more shriller the sound. Loudness determines the amplitude of sound. Higher the amplitude, more louder is the voice, and lesser the amplitude, less uh, feeble is the voice. Feeble. Timbre. Timbre is basically the quality of sound. Now, say Rituraj sir's timbre is not as, or I'd rather say Arijit Singh's timbre is not as good as Rituraj sir's. So we have a different quality of sound. I have a different quality of sound. Arijit Singh has got a different quality of sound. Me and Arijit Singh, we do a concert together, say, and we are singing the same song at same frequency and same loudness also. Our amplitude is same, our frequency is same. Still, we both will sound different, and that is called quality of sound. All right. So timbre is basically specific about the source. So timbre depends upon the source of sound also. So Arijit Singh's source is different and my source is different. So both of us are going to have a different timbre. Though we have the same frequency and pitch. Why? Because timbre depends only on the source of sound. Then we have intensity of the sound. Intensity basically tells us about energy of the sound, and it depends upon the energy passing through a given area. You don't have to go into mathematical concepts of this thing. Speed of sound, we just spoke about that. Speed of sound is equal to wavelength into frequency, because speed is equal to distance upon time. Distance is, say, wavelength, then time taken to complete one wavelength is capital T, so it is lambda upon T, and 1 by T is frequency. Find the frequency of a wave whose time period is 0.002 seconds. So frequency is 1 upon time period, and time period is, this is T. It is 1 upon T, 0.002. I'll multiply numerator and denominator by 1000 so that the denominator becomes 2. So it is 500 Hertz, the first question. Second one, find the time period of a wave whose frequency is 400 Hertz. So time period is equal to 1 upon frequency is 1 upon 400. So it will become 1 by 4 is 0.25 divided by 100. Right, because I have multiplied 4 into 100 and 1 by 4 is 0.25. So it will become 0.0025 seconds, because time period is in seconds. A wave source produces 20 crests and 20 troughs in 0.2 seconds. So 20 crests, first crest, second crest, third crest, fourth crest, and so on. In 0.2 seconds, find the frequency of the wave. So 20 crests means how many waves are completed? In one wave, there is only one crest. Alright, and one trough. So 20 crests means there are 20 waves produced in 0.2 seconds. So in 0.2 seconds, the number of waves produced, number of oscillations which have taken place is 20. So in 1 second, how many oscillations are going to take place? That is 20 upon 0.2. So it will become 200 upon 2 is equal to 100. So this is the number of oscillations in 1 second. So 20 crests and 20 troughs are basically telling us that there are 20 waves or 20 oscillations have taken place in 0.2 seconds. But frequency is number of oscillations in 1 second. So I am finding by using unitary method that in 0.2 seconds 20 oscillations took place. Then in 1 second how many oscillations will take place? That is 20 upon 0.2. And that will come out to be 100. So it will be 100 Hertz. That's the answer. Alright, now last question, this 12.1 is based on velocity of wave. What have they given? Let us see the data given to us. They have given 2 kilohertz. The frequency is 2 kilohertz. Kilo means 1000. So it is 2 into 1000 Hertz. Wavelength is 35 centimeter. Bacho, we have to always consider SI units, that is meter, kilogram, and seconds when it comes to calculation in MKS system of units. So this is 0.35 meters. How long will it take to travel 1.5 kilometer? So they are asking us time. For time, distance is given. We need to find time. We know that distance is equal to speed into time. Time they are asking, distance is given, but how much is the speed? So first we'll be using frequency and using wavelength. We are going to find the frequency. You see, what is the frequency now? So speed upon wavelength will give us frequency. How much is the speed of sound? It is, we don't know the speed, sorry, my bad. speed is equal to wavelength into frequency. How much is the wavelength given to us? 0.35 meters, because 35 centimeter is 35 upon 100, which is 0.35 meters, into frequency is 2000. By using these two zeros, I am going to eliminate the decimal first, so it's becoming 35 into 20. 35 into 2 is 70, and one more zero, that is 700 meter per second. This is the speed of the wave coming out to be. Since the speed of wave is 700 meter per second, total distance is 1.5 kilometer. So time will come out to be distance upon speed using this formula. So distance is 1500 meters, because 1.5 kilometer, if I multiply by 1000, it will become 1500 upon distance upon speed. Speed is how much? We just calculated it to be 700, 0 gone. So 15 upon 7, the time is 7 2s are 14, 10 in 7 1s are 7, 30, 7 4s are 28, about 2.14 seconds. That is it. Alright, then intensity of sound is measured in decibels. Alright, and greater the intensity, greater the decibels. So some data is given here. You just need to understand that how much noise you people produce, and how much is the noise produced by a jet engine or a rocket engine. This we have already done. That speed of sound depends upon temperature. Temperature rises, speed of sound increases. It depends upon the nature of material, fastest in solid, lesser in liquid, and least in gases. It also depends upon humidity. See, when humidity comes in air, that means what? More moisture is in air. Now air is becoming certainly semi-liquid. So obviously we know that speed of sound is more in liquid. So in a humid air, the velocity of sound will be more. There is a term called supersonic. Supersonic is when something travels faster than the speed of sound, is called supersonic. Some jets are supersonic, 700 kilometers per hour. Reflection of sound. Now sound also follows the same laws of reflection as the reflection of light. That is, the angle of incidence is equal to angle of reflection, and the incident ray, the reflected ray, and the normal, this is the normal, the incident ray, the reflected ray, and the normal all lie on the same plane at the point of incidence. That means they will all lie on the same plane, and angle of incidence and angle of reflection are always made with the normal. So if the sound comes and strikes something, it will get reflected in such a way that this I and this R are equal. That is all about the reflection of sound. There is certain phenomena which is based on reflection of sound. Now suppose there is a big hall and I say my name, Rituraj, and after some time I again get to hear my name, Rituraj, Rituraj, and after that there is another phenomena, Rituraj, 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 Rituraj. So you're hearing the same sound again, when rather you produced it only once, but you are again able to hear the same sound again. This is called echo. The echo is the phenomena of repetition of sound by a source because of reflection of sound. And reverberation is multiple echo. In simple terms, I can say that reverberation is multiple echo. Echo is the cause of reverberation. What is echo? It is the phenomena of repetition of sound by a source by reflection from an obstacle. If I say something and I'm quiet, then I'm able to hear the same sound again. Then this phenomena is called echo. And multiple echo is called reverberation. And you must have not experienced this in your classroom, because there is something called persistence of sound. Or I'll rather say that your brain takes about 0.1 seconds to process a sound. In the interval of 0.1 second after hearing the sound, your brain will not be able to process any other sound. So if the same sound produced by you is getting reflected from multiple walls around your room and it is reaching your ears within 0.1 seconds, you will not be able to hear the sound again. And that is why at home or in the classroom you are not able to hear the sound. That is because the sound is coming back to you in 0.1 seconds, within 0.1 seconds, and your brain is not able to perceive that sound. But on the contrary, if it happens that the sound comes back to you after 0.1 seconds, then you are able to hear the sound again, and that is called echo. when the same sound is reheard. Now, what is the condition for echo? So now we know that sound must come back after 0.1 seconds. Now say Rituraj sir is speaking something and there is a obstacle here, the sound goes and it comes back, but I'm not able to hear it. So what I'm doing is I'm increasing the distance slowly, gradually I'm increasing the distance. A stage comes when I am able to just hear my sound back again when the obstacle is pushed far away. So I am asking you, how far is the obstacle from me? That is what we are going to calculate here. So when the sound went, it traveled a distance d. When it came back, it has traveled distance back again, that is 2d. Total distance 2d. With what velocity did the sound travel? Say, let us say the sound at the normal temperature at 21 degrees Celsius is say 344 meter per second. Okay, because we know that distance is equal to velocity into time. Now in which time, what minimum distance should I keep the obstacle that I am able to hear it back again? You just said that, sir, if the sound is coming back to our ears after 0.1 seconds, we'll be able to hear the echo. So I'm going to take the time as 0.1 second. So which implies 2d comes out to be 344 into 0.1 will become 34.4, which in turn d will become 34.4 upon 2 and d comes out to be approximately 17.2 meters, but that will depend upon the velocity of sound. Here we have taken the velocity of sound as 344 meter per second. If I would have taken the velocity of sound to be 330 meter per second, the answer would have been different. Alright, in general, so that is what these people have also used here, that the minimum distance of the obstacle at normal temperature and pressure should be about 17.2 meters so that the sound goes and comes back, travels a distance 2d in 0.1 seconds. If the distance of the obstacle from me is more than 17.2 meters, I'll be able to hear the echo back again. This is called echo of sound. Now, if I talk about a big movie hall, so there are many walls on the movie hall. So it might so happen that the sound goes and gets reflected from the first wall and then comes back to me, then it gets reflected from the wall which is far away from me, and then it again comes back to me. So I'm able to hear the same sound again and again and again. That is called reverberation of sound. Multiple echo is reverberation. In reverberation, the sound is persistent for some period of time. You must have seen this. Hello. Echo is hello, 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 hello. And reverberation is hello. That is reverberation. Because it is coming back to you again from multiple directions. Alright. Now what is our audible frequency range, audible range of hearing? It is 20 Hertz to 20,000 Hertz. The 20,000 is written as 20 kilohertz. The sound below 20 Hertz is called infrasonic sound, and dogs and dolphins can actually hear this thing. The sound above 20,000 Hertz is called ultrasonic, and bats and whales use this for echolocation. They are using this for echolocation. So what are the uses of ultrasound? Ultrasound is used for generating images of fetus. It is also used to detect cracks in pipes and metal blocks, metal box. Ultrasonic sound is also used for echolocation, to locate something. Now see, suppose an ultrasonic sound, this is a ship. There is a special thing of ultrasonic echolocation, that is sonar, which is basically the ships use this to find out enemy ship and also depth of sea. Now say suppose this is the ship, this is the base of the sea, and I want to know the depth. So what will happen is I'm going to emit an ultrasonic wave. It is going to get reflected back again. So say the depth of the sea is d. We have one universal formula in this chapter, that is 2d is equal to v into t. I want to find the d. So what will it do? The sound is emitted, the sound gets reflected back, it comes back to me in say some time t which is recorded. We know the velocity of sound in water, we have just studied that is something around 1450. Yeah, around of 1500, say let us say 1500. So we know the velocity of sound as 1500 meter per second. Time, say we have the emitter, when it emits the sound, the ship is equipped with a receiver also which is able to note down the time automatically. It is going to detect, the receiver is going to detect the reflected sound and is going to note down the time. Time also is known. Can I not find the distance? This is what bats also do. So bats are going to emit an ultrasonic sound, And ultrasonic sound travels very quickly because it has got very high frequency, very high energy, and the ultrasonic sound gets reflected from the obstacle, and the bat senses it, and the bat now precisely knows this d. So this mathematics, this d is what? The distance of the obstacle. That is how it echolocates. This is called echolocation. Then ultrasonic sound is also used to clean those parts of the machinery which is not reachable. So machine parts which are not reachable. There is one more thing in this chapter, that is about multiple reflection of sound. Now what is multiple reflection? When the sound waves are getting reflected from multiple directions, that is called multiple reflection of sound, and this is what we use in concert halls also. Alright, let me see a blank page. Now you see, suppose there is a concert hall, a singer is singing here, Rituraj sir is singing in a concert hall, and there are people seated in in these places. Now the one who was sitting nearer to me can hear to me easily. So what I'm going to do, I'm going to make the backside of the concert hall curved. So what will happen when I'm speaking, when I'm singing, the sound is going to get reflected in multiple directions, and it is going to reach my audience. Directly also it's reaching, and by getting reflected also it is reaching each and every corner. Same thing goes with ceiling also. I am singing here, the audience is seated here, these are the seats. So what is happening is that the reflection of sound is taking place from the curved ceiling, and because of which it is reaching each and every person. Multiple reflection of sound is also used in loudspeakers. So what is happening? You are putting sound here. What is happening? They are getting reflected. Multiple reflections is taking place, and these sound waves are overlapping, and the sound becomes more. Overlapping of sound here is taking place. We will be studying about interference in, the addition, superposition of waves in class 11. But as of now, I want to tell you that when you try to speak in a megaphone, what happens? It basically amplifies your voice. That is because of multiple reflection of sound taking place, and the sound waves are basically resonating, and it makes the sound louder. That is how the megaphones generate more voice. We have done this experiment in classroom also. So this is to boost multiple reflection. This is to boost multiple reflection. This is based on multiple reflection. Then doctors use stethoscope also, if you must have seen. So stethoscope, what is happening? That we can hear a heartbeat. So what is happening? That stethoscope consists of a tube, and in this tube, what is happening? The multiple reflection of sound is taking place from one source. When this multiple reflection takes place, the sound waves, multiple number of sound waves coming out from that organ are getting amplified. So basically this also is doing nothing, but it's causing multiple reflection and amplification of sound. That is why in stethoscope you can hear loud voice of your heartbeat. But sometimes multiple reflection is bad also. That is bad because when you are in a concert hall and the multiple reflection is taking place, or you are watching a movie and multiple reflection is taking place, or echo is taking place, or reverberation is taking place, so that is causing noise. You're hearing a dialogue and the next dialogue comes up, and the echo comes again. So they are both overlapping. So what we are going to do, we are going to first use of foam, use of fireboard. So fireboard is basically ply or some soft, not fireboard, I'll rather say fiberboard. Fiberboard. Fireboard is the ply which they use these days. You can even use ply. You can use of curtains. Use curtains on the walls. You must have seen in movie halls that they put velvet type of cloth on the walls. They cover the walls with velvet type of cloth so that the sound will not reflect, but it will absorb sound. And one more thing, that the reflection of sound is more prominent from a hard surface. The harder the surface, more prominent is the reflection. The smoother the surface, less prominent is the reflection. The same thing you can tell if I throw a tennis ball on a wall, it gets reflected very quickly. If I throw the same tennis ball on a say wooden couch or a soft surface, a Dunlop or a gymnastic bag where we fall, if you throw the ball is not going to jump back. The same thing happens with sound also. If it falls on a softer surface, it will not reflect back. So we try to, even the staircases, covered with carpets. In a movie hall you must have seen, in concert halls you must have seen, so it absorbs sound. Even the reflection from staircase is not taking place. Then we are using certain soundproof materials. So what they do is they will try to put some foam on the walls, or even egg tray is the simplest way of absorbing sound in a room. So that will prevent reflection, multiple reflection, reverberation. I hope this much is clear to you, and if there is any other query, you can directly write it to me in the comment box. Kindly like and subscribe and share the word with people who need it. Thank you for hearing out. Take care.